Hi everyone, welcome to our video about optimization problems. And so this is going to be very similar to the last video where we were just finding minimums and maximums of curves, except now we're just going to sort of add a little bit of a real-world modeling, real-world twist. So it's going to feel more applicable to real life, I guess. And the idea here is that in an optimization problem, you're asked to find the optimum values of a function. But the optimum values is going to be either a minimum or a maximum, depending on what you're trying to do. So like the optimum cost would be the minimum cost, right? And the optimum profit would be the maximum profit. And so depending on the situation, you either want the minimum or the maximum. Now again, I've said this in the last video, but you should report your answer as both the location and the value, sort of in a coordinate pair. Anytime you're doing any of these minimum or maximum problems, definitely go ahead and give the full answer, which is both the input and the output to the function, or both the x and the y value. So example number one, basically we're just going to teach you this concept through examples. But example number one says, you are the CEO of a disposable camera company, and you want to optimize the company's profit. So here, optimizing profit would mean the same thing as maximizing profit. Profit is a good thing, and so you would want to maximize in this case. Now, spending more money on Facebook ads drives more customers to buy your cameras. We're going to call lowercase s the number of cameras sold per month, and lowercase m is going to be the amount of, or the number of advertising dollars that you spend during the month. And we have this function that relates s and, s being the number of cameras sold and m the advertising dollars, so we say s is a function of m. And that function is 10 times the square root of m plus 50. Now each disposable camera costs $4 to make, but sells for $15. Also, your business has the overhead cost of, by the way, overhead cost just means costs that aren't related to the number of cameras sold, right? We say the cost is a variable cost if it is proportional to the number of cameras sold. So like our variable cost is $4 per camera, but then our fixed cost, or our overhead cost, that is things that we have to pay every month regardless of how many cameras we sell. So like regardless of how many cameras we sell, every month we have to pay employees, we have to pay for the water and the garbage and the electricity and the gas bill. And so our overhead is going to be $900 per month. The question states, what is the optimum amount of money to spend on advertising in dollars per month? And when you do spend the optimum amount of money on advertising, how much profit results? And so we'll let P be profit. So, a lot to unpack here in this question. It's a little bit complicated. Remember that profit is just equal to revenue minus expenses, where revenue is the amount of money your business is bringing in, and the expenses are all the things you have to pay for. Now, our expenses, like I said, they come in both variable cost and fixed cost, or we also call overhead fixed cost. And so when we go about calculating our profit here, our revenue is going to be $15 per camera. So remember, I'm using lowercase s to represent the number of cameras sold. And each camera sells for $15. So my revenue is just 15 times the number of cameras sold. Minus the expenses, and among my expenses are $4 for every camera sold, because each camera costs $4 to make. That's my variable cost. Minus 900, and it's just plain 900 because it's invariant based on the number of cameras sold. This is my fixed cost per month. So this is my formula for profit. But how many cameras are we going to sell per month? Well, the number of cameras we sell per month is a function of the advertising dollars, right? And so we write S is equal to 10 square root M plus 50. And making that substitution here in my profit equation, I get that this is going to be 15 times 10 square root M plus 50 minus 4 times 10 square root M plus 50 minus 900. And now you can see I have an equation that gives me my profit as a function of advertising dollars spent. So P is profit and M is advertising dollars, right? And so this is just a function P of M. And we can do some simplifying here, and we should do some simplifying here. So distributing that 15, this is 150 square root M plus 50 times 15, I think is 750. Minus, distributing the 4 gives me 40 square root M minus 200 minus 900. And so collecting like terms here, I have terms with a square root M. So this is going to be 110 square root M. And in terms of my constants, I have 750 minus 1100. So that's going to be minus, I'm really struggling with the math here, 350. 1100 minus 750 would be like, yeah, that should be 350. If I got that wrong, send me a message so you can go back and correct it. Yeah, so this is giving me profit as a function of advertising dollars spent. Except that I actually forgot one really, really, really important thing. And maybe it was easy to go along sort of with my argument here, and so you were sort of nodding your head in agreement, but think for a moment, what is the one thing that I've ignored in my profit equation? The one thing I ignored in my profit equation is that I had, of course, my variable cost for my cameras as an expense. I had the fixed cost of paying my utility bills and paying my employees. But there's one other expense that is really easy to forget about, or really easy to ignore. And that third expense is going to be advertising dollars. That's not supposed to be M factorial. I was just very excited. So lowercase m is the advertising dollars per month spent. Yeah, and so let's just go ahead and add that. So I'm going to write minus m, because any advertising dollars would be subtracting from my profit at the end of the day. But anytime I spend advertising dollars, that's reducing my amount of profit by that many dollars. And so I have to subtract lowercase m at each stage. And now this function is the correct function for profit. Okay. So we're moving along. We're asking, what is the optimum amount of money to spend on advertising? And so basically our question here, just to rephrase it, is what m gives the maximum value of p, which is profit. And so you maybe remember that the maximum or the minimum has to occur at a critical point, and critical points are the places where you take the derivative and set it equal to 0. So let's take the derivative of our profit with respect to advertising dollars, and notice that I can rewrite my profit equation like 110 times m to the 1/2 power, because the square root is just the 1/2 power. And now I can just use my power rule and write this is going to be 110 times 1/2 times m to the negative 1/2 power. When I have minus 350, that goes away in the derivative, because a derivative of a constant is just 0. And where I have minus m, that's just going to be minus 1. So this is my derivative function, and we're going to set that equal to 0 to find my critical points. Okay. Now, looking at this equation here, given in green, I can add 1 to both sides, and this is 1, and then on the left side, simplify this a little bit, and I have 1/2 of 110 is 55. And then where I have m to the negative half power, that's just dividing by square root m. So I might multiply both sides by square root m, and this is saying that square root of m is equal to 55. And then to find what m is, I just need to square both sides of my equation. So 55 times 55 is not something I know off the top of my head, but we can quickly find it. It's going to be 2,500 plus 250 plus 250 plus 25. So to me that looks like 3,025. So the answer to this problem is if you you want to maximize the amount of profit you spend or that you're bringing in with your business, this is the amount of advertising dollars. And maybe you would say, hold on, aren't you jumping to conclusions a little bit early? And you'd be right, because all we did was find a critical point by setting the derivative equal to 0. And what we still have to do, if we want to be extra sure, is let's make sure this critical point is actually a maximum of that P profit and not a minimum or an inflection point, right? Because not every critical point is a maximum or minimum. Not every critical point is a maximum. Sometimes critical points can be minimums, sometimes they can be inflection points. So if we want to make sure that this is a maximum, what we have to do is take the second derivative of P with respect to M. And so taking the second derivative of P with respect to M, I just take the derivative of the derivative. And so where I have that -1, that's going to be a 0 because the derivative of a constant is 0. And then using my power rule again, I'm going to have 110 times 1/4, or -1/4. Because I brought down the -1/2 power as a constant multiple. And this is going to be times m to the power -3/2. And I can just leave it like this, and what I want to do is evaluate what is that second derivative evaluated at the point m equals 3025, evaluated at my critical point. Because remember, when I figure out the second derivative, I'm going to look at the positive or negative sign, and that's going to tell me whether we're concave up or concave down. And think to yourself for a moment, do I want this to be concave up at the critical point or concave down at the critical point? So the answer is we want it to be concave down at the critical point, because a concave down function at the critical point is a maximum, whereas if you have a concave up function, the critical point would be a minimum. So we're looking for a concave down function. That means we actually want the second derivative to be negative. And let's just double check and make sure my second derivative is negative, and that's going to be 110 times the -1/4 power, so I'll put times -1/4 times m, which is now 3025 at the critical point, to the power, open parentheses, -3/2. And so this is a really, really small number, but it is negative. Notice this. So even though it's a very small number, it is a negative number. And so that tells me that we are concave down there. So since it's negative, we're concave down, and that means this is a maximum. And that's exactly what we want. So that's the amount of advertising dollars that gives us the maximum value. And what is the value for profit when I spend exactly $3025? Well, we go back to our profit equation and we just evaluate P at the M value, 3025. And let's see what we get. So that's going to be 110 times 3025 to the power 1/2. So remember the square root is just the 1/2 power, minus 350 minus the number of advertising dollars, which is 3025. That gives me a profit of $2,675. So $2,675. So if I was going to report my answer as a coordinate pair, let me make a little box over here for my answer. The coordinate pair being then advertising dollars spent, that's my independent variable, comma, the profit made, that would be my dependent variable. This is going to be, for spending $3,025, I expect a profit of $2,675. That's how you would report your answer as a coordinate pair. And this is the the most full explanation of what that maximum is, both the location of the maximum and what the actual maximum value of the profit could be. So these are longer problems. As you may have noticed, we spent about 15 minutes on that last one. Example 2 says, the speed of a runner in miles per hour on a straight trail is modeled by this, where m is the runner's distance in miles from the start of the trail. What is the maximum speed of the runner between 0 and 3 miles? Now, what distance from the start of the trail does she hit her maximum speed? So, we have another closed interval here. And remember, with closed intervals, I have to try the start point and end point of the interval. And so the candidates for maximums are going to include 0, 3, and whatever critical points that I'm going to find. So this is the function that describes the speed. It is 1/10 times negative 2m cubed plus 9m squared minus 12m plus 7. So if I want to find the derivative, well, I just have to use my derivative power rule, it looks like. So this 1/10 is just a constant multiple, so I leave that alone. And then this is going to become negative 6m squared plus 18m minus 12 plus 7. Oh, and by the way, the plus 7 goes away in the derivative, doesn't it? Because the derivative of a constant is just 0. Now, critical points, if I'm trying to find critical points are just where I set the first derivative equal to 0. So I set that first derivative equal to 0, which means that negative 6m squared plus 18m minus 12, all times 1/10, that has to be equal to 0. But if I multiply both sides of my equation by 10, 0 times 10 is just 0, so I can actually just get rid of this. And also, I could multiply I could divide both of my sides of my equation by 6, and this just becomes negative m squared plus 3m minus 2 after I divide everything by 6. 0 divided by 6 is still 0. And then I like quadratics where the leading coefficient is positive 1. And so let me, instead of dividing by 6, divide by negative 6, which would give me that. Now, factoring this, I believe should give me m minus 1 times m minus 2 equals 0. So there's two values for m that give me a critical point. My critical points would be positive 1 and positive 2. Those are going to give me the zeros of my derivative. So my candidates are 0, 1, 2, and 3. The green here, again, is because these are critical points. So critical points, remember, can either be maximums, minimums, or inflection points. And I wrote in purple these candidates because these are the boundaries of my closed interval. But I have to check out all of these candidates by plugging them in to my function and seeing what value I get. So if I write f evaluated at 0, f evaluated at 3, f evaluated at 1 and f evaluated at 2, I can find the speed of my runner at each of these points. And then I just look and see among these four options, what is the maximum speed. So if I plug in m is equal to 0, this is just going to be 7. If I plug in m is equal to 3, that's going to be a little bit harder. Maybe get a calculator out for that one, just because I don't want to waste a lot of space here. If I plug in m is equal to 1, I've got -2 plus 9 gives me 7 minus 12, which is -5, times 1/10, so that's -½ So that looks like it's going to be about 6.5. And then again, for 2, I'll grab a calculator. So let's evaluate the function at m is equal to 3. And I get 1/10 times, open parentheses, -2 times 3 cubed plus 9 times 3 squared minus 12 times 3, close parentheses, plus 7. Oh, let's see what I did wrong. Oh, that negative, that's actually a minus, and my calculator's picky. That minus needs to be a negative, so that should fix it. There we go. Okay, 6.1 is what I get when I evaluate that at 3. And then when I evaluate this same function at 2, I should end up with 1/10 times -2 times 2 cubed plus 9 times 2 squared minus 12 times 3, close parentheses, plus 7. Oh, that shouldn't be 12 times 3, that should be 12 times 2. Oops. I wish I knew how to copy and paste, but I don't. So here we go. Gonna have to type it in all over again. So 1/10 times, open parentheses, -2 times 2 cubed plus 9 times 2 squared minus 12 times 2. And I see that I've messed up a lot of this, so. Calculators can sometimes be frustrating. Here we go. 12 cubed plus 9 times 2 squared minus 12 times 2, close parentheses, plus 7. I'm just going to check before I hit enter. And that should be right. So it's 6.6. And it looks like among my 4 candidates that the very maximum value is this one. At 0 miles, so when the race first starts, it looks like the runner is running 7 miles per hour, and so this is going to be my maximum. So that would occur at the coordinate pair 0, 7. Okay. Let's see if we can do one more. And I think this is going to be the fastest one of all so far. But this problem says a rectangular area is to be enclosed by a long pre-existing wall on one side. So let's make this the wall. And fencing on the other 3 sides. So we have some kind of fencing here. If 18 meters of fencing is used, what is the maximum area that can be enclosed? And so let's call this side of the fence the width, and since this is a rectangular area, let's call that the width. And that means this is going to be the length, and this is also the same length, since this is a rectangular area. I know that the area of a rectangle is just length times width, and the amount of fencing used is 18 meters, but the amount of fencing used is going to be 2 times the width plus the length. Okay, now we've got 2 equations here, but we actually have 3 unknowns. Let's see if we can try to untangle this anyways. And the way we're going to do this is let's solve for L first. And so if I just solve for the length, this is going to be 18 minus 2W. And I'm going to take this definition of L and then plug it in here for L. And so that makes my new area equation just 18 minus 2W, which is the length, times W. So area is going to be 18W minus 2W squared. And if I want to find the maximum area, finding the maximum sort of means that you have to find critical points first and then test if the critical points you found are maximums or minimums. So to find the critical points, we're first going to take the derivative of area with respect to width. And so the derivative here is going to be 18 minus 4W, because that's just derivative power rule on each of those terms. And to find critical points, I set that equal to 0. So setting that equal to 0 gives me 4W equals 18, and divide both sides by 4, and I get that the width should be 4.5 meters. And that's for a critical point, right? So is this critical point really a maximum? Well, let's take the second derivative. So the second derivative of area with respect to width would just be the derivative of the derivative. So 18 goes to 0 because that's just a constant, and then negative 4W becomes negative 4. So a negative second derivative, that tells me that I am concave down. And where I have a critical point for a concave down function, that critical point is the maximum. And that's exactly what we wanted to find. We wanted to find the maximum. So my width that gives me the maximum area is 4.5. What does that mean my length is? Well, I have length as a function of width. So this is 18 minus 2 times 4.5. That's 18 minus 9. Because 2 times 4.5 is 9. And 18 minus 9 is 9, so this length is 9 meters. And so I know the dimensions now of fencing that give me the maximum area. And then 4.5 times 9 takes me a moment to think about, but I think that's 40.5 meters squared. So if I were reporting my answer as a coordinate pair, I would answer that I guess the width and the area, the independent and dependent variables here, are 4.5 for the width and 40.5 for the area. Okay. Also too, if this were an open-ended question on an exam and you just labeled the diagram with the correct values for width, length, and area, that would be full credit, right? So don't feel like you have to know exactly how to report your answer as a coordinate pair. If you do a good job communicating to me that you understand both what input values give you the maximum and what the maximum value is for a given optimization problem. And I have more examples to work, but this video is already 30 minutes long, so maybe I'll just leave these examples to you to get a little bit of practice in. And as a warning, these last two examples are really tough. And so if you can't work these examples, don't sweat it too much. Just maybe work some examples from the textbook, because I think those examples are a little bit easier than this one in example 4. And then the last one I'll show you is this one in example 5. This is one in example 5 being an extreme challenge where I would be, very proud of you if you could figure this one out. Okay, y'all have a good week.